Okay, so to continue, the next step in the scientific method is after establishing a tentative answer called the hypothesis, next step is to create predictions or to predict what would happen if you're going to experiment on a possible setup in order to answer the post question in the hypothesis. A prediction is actually a guess, not any guess, but is an educated guess of what possibly would happen once we actually proceed with setting up an experiment in order to answer our hypothesis. Now, since the idea here is the hypothesis will never be answered, not unless that we conduct an experiment. So the obvious next step for the scientific method is to establish or to conduct experimentation. And lastly, the result of the experimentation is to create a verification of the answer in the hypothesis stage, leading to what we call a conclusion. Just what I have presented to you, the hypothesis is simply a tentative explanation of a given phenomena. It is an educated or an intelligent guess. A model, on the other hand, relies on scientific assumptions. It has few experimental evidences. It is easily contradicted by several other experiments and is not universal. Model is not the like a model that we know that the person that wears clothes, but actually a scientific model is more of an idealization of a particular situation. So, for example, an example of model that we use in physics is the idealization of what we call free fall or free falling bodies. A free falling body is a body that is moving along the vertical by virtue of the influence of gravity alone. So the model is that only the force of gravity which acts along the vertical acts on the object that is thrown upward or is falling. We disregard the effects of air resistance. So, but of course, we know that in a real setup or a real situation, we could not actually eliminate the effects of air. Thus, the idea for a freely falling body, in order to apply scientific assumptions, we make use of an idealized model wherein we remove several effects of other factors. uh, that is the reason why that model is considered not universal in this sense. Now, what is a theory? A theory is simply an explanation supported by several experimental evidences. A theory is flexible enough to be modified. So, an example of a theory is a common or a popular example for a theory is called the Big Bang theory, wherein the Big Bang theory actually tells us the or explains us the evolution of the universe, how it came about from the very beginning of the expansion of this primordial ball of energy. A scientific law, on the other hand, these are actually theories that stand for a very long time. They can be experimentally be proven on several occasions. They are they are uniform and is universal. An example of a law is the law of gravity. Now, between a theory and a law, so explain. Going back again with the steps of the scientific method, a hypothesis is supposed to be verified by experimentation, leading to a particular conclusion, and a conclusion that explains the observed phenomena. Now, this explanation could be upgraded into either a law or a theory. So, what is the main difference between a law and a theory? Well, the main difference between a law actually answers the question what, while a theory answers the question why. So whenever we are to explain a particular phenomena, whenever we are asking what, we are actually looking for a law, whereas when we tend to look for an explanation for the question why, we are actually looking for a theory. So, for example, the law of gravity. So we ask the question, what is gravity? While in the theory, for example, the Big Bang theory, we ask the question, why did the universe came about? Okay, so next in our discussion is scientific notation. This is a very basic skill in physics. Writing a number. In physics, we usually encounter numbers that are very, very small, numbers that are very, very large. So it is worth noting that we have the scientific notation as a method of writing a number in shorthand. So this is a method of writing very large or very small numbers as multiplication with integers with powers of 10. Now, and units. And units. In physics, we usually encounter what we call physical quantities. These physical quantities are any numbers, any quantities that are described by a number to which we attach a particular unit to describe that physical quantity. And a physical quantity is a description of the physical phenomena that we usually observe, and a physical quantity quantifies that physical phenomena. Now, there are quantities that are so fundamental that we cannot um, derive them physically in terms of other quantities. Such quantities are basically based on operational definition, and they are considered as quantities that has direct measurements. So in order for them to be described, the only way to describe them is to measure them. And these quantities are called basic quantities, and there are systems of units that we use in the world. We have defined several of these quantities, and we will be discussing them on the next slide. Okay, so in the world today, we are actually using two sets of standards of measure. One is the English or the British system, and the other one is called the metric system or the international system of units. The metric system and the international system of units are almost the same. The metric system was converted as the international system of units in 1960. The English system is usually or traditionally used in the United States and other countries that follow the traditions of the United States. But currently, almost all countries, even the United States, the English systems is slowly being replaced in such countries, and it is being replaced by the metric system, since the metric system is basically compounds on the idea that the system of units is used scientifically. So examples of units that we usually encounter in the English system are the following. We have the inch, the yard, the mile for distances, pint, quart, gallon for volume, ounces, pound, and ton for weight. Now, as mentioned before, the metric system or the international system of units, these are the units that you usually use for scientific measurements. The metric system, of course, the English system was developed by the British, whereas the metric system was developed by the French. The metric system uses prefixes in order to indicate different powers of 10. Examples that we usually encounter in the metric system are the meter for the length, liter for the volume, gram for mass. The international system of measurements, there are specific choices of metric units for use in scientific measurements. It was adopted on the 11th General Conference of Weights and Measures in 1960 for scientific purposes. Its units are called the SI units from its acronym of the French equivalent for the International System of Units. Now, what you see on the slides are the unit prefixes that we usually attach to the basic unit in order to indicate the magnitudes or degrees of factor for that particular quantity. So, for example, we have 10 to the 24 for iota, uh, 10 to the 9 for giga, 10 to the 6 for mega, 10 to the 3 for kilo, and so on. For smaller degrees of measure, we have the following. The exponents becomes negative for those factors. So prefixes that we usually encounter in smaller units, we have the following: centi, for example, micro, milli, nano, and so on. Now let me introduce to you the first of the basic quantities. First is time, which has the basic unit for us the second. The unit of time was defined as a certain fraction of the mean solar day, and this was adopted during the times from 1889 to 1967. But from 1967 up to present, the definition of time was revised and was based on an atomic clock using session atoms. From 1967 and so on, 1 second now is defined as the given number of cycles of the radiation emitted by this cesium atom. Next would be the basic quantity length. In the SI system of units, the basic unit attached for the description of length is the meter. Now, the meter is defined as the atomic standard for meter was established using the wavelength of the orange-red light emitted by krypton atoms. This was adopted by year 1960. But on November 1983, the meter was again revised in terms of its definition. From 1983 onwards, the meter was defined as the distance that light travels in a vacuum, which is 1 over 299,792,458 second of this spectrum of light. The speed of light in vacuum is the reciprocal number, 299,792,458 meter per second. So getting the reciprocal of the speed of light gives our basic definition for the distance traveled by light, and this is defined as the meter. Now, the third basic quantity is mass, and its SI unit is the kilogram. The kilogram is defined to be the mass of a cylinder alloy of platinum iridium kept by the International Bureau of Weights and Measures at Sèvres near Paris. Another basic quantity in the international system of units for, but this time for temperature, is the Kelvin, expressed here as capital letter K. So the freezing point of water in the Kelvin scale is 273 kelvins, whereas the boiling point of water is 373 kelvins. Take note that the freezing point of water in the Celsius scale, the freezing point of water is considered as 0 degrees Celsius, whereas the boiling point of water is 100 degrees Celsius in the Celsius scale, and equivalently in the Kelvin scale, this is simply 273 kelvins and 373 kelvins respectively. Now, I have discussed to you the four basic quantities of time, length, mass, and temperature, but the complete set for the international system of units for base units are the following as seen in this table. Fundamental units where other units are, these are the fundamental units where other units are derived. Remember that these are basic quantities. What is meant by fundamental units where other units are derived, meaning any combination of these quantities is considered as derived quantity, and these are the basic quantities. Okay, so the physical quantities, we have the mass, length, time, temperature, amount of substance, electric current, and luminous intensity. The corresponding units for each are the following: kilogram for mass, meter for length, time for second, Kelvin for temperature, mole for the amount of substance, ampere for electric current, candela for the luminous intensity. And on the third column of the table, we have the following symbols to represent these base units. Take note that the International System of Units has the monopoly of electrical units. There are no electrical units defined in the British or the English system. Only the International System of Units has units for electrical or electrical units or electrical quantities. Now, as mentioned before, these are called the basic quantities. Any combination of the basic quantities to form another quantity is called a derived quantity. So examples of derived quantities that we will usually encounter as part of the International System of Units. For example, we have area, volume, density. There are other quantities that we will usually encounter, such as speed, velocity, acceleration, forces, and so on. Okay, so next would be uncertainty in measurements. So let us first define what are exact numbers. Exact numbers are those numbers that are known exactly. Example, the number of count of nouns and conversion factors. Inexact numbers, on the other hand, are those numbers whose values have some uncertainty. Numbers obtained by measurements and very large numbers even if they represent count nouns. Now, significant figures. The method with which the scientists represent the accuracy of the measuring instrument used to obtain the recorded data, and this is called significant figures. Now, let us go through the rules of significant figures. Number one, exact numbers are considered to have infinite significant figures. So what does that mean? Exact numbers are considered to have infinite significant figures. So for example, if we express a number such as 23, a number 23 is exact. For example, the number 23 represents the number of persons. Number of persons, the number of persons is a count noun. 23 persons. So when we have exact numbers, then it is considered that these exact numbers have an infinite significant number of figures. Rule number two, all non-zero digits are significant. So in our given example, the number 23, both 2 and the digits 2 and the digit 3 are non-zero digits and they are considered significant. Zeros between two non-zero digits are significant. For example, if you have the number 203, in the example 203, you have a zero digit in between 2 and 3. So since 2 is a non-zero digit and is significant, 3 is also a non-zero digit and is also significant. The zero that appears in between these two numbers is considered significant, since you cannot express the number 203 if you consider the zero in between as insignificant. Therefore, that number is significant. Okay, next, rule number 4, zeros at the right end of the number and the right of decimal place are significant. Zeros at the right end of the number and right of the decimal place are significant. So what does rule number 4 mean? So for example, you will have the number 23. The number 23 can be written as 23.0, 23.00, 23.000, or any number of zeros that we can attach to the number 23. Any number that is attached to the number 23 as part of the decimal point is considered significant if you're going to write that number accordingly. So for example, 23 has two significant figures. The number 2 and 3 are significant. If you attach a 0 to the right of the decimal point, meaning you write down 23 as 23.0, the number of significant figures is no longer 2 but is 3. So 23.0 it has 3 significant figures, whereas the number 23.00 has 4 significant figures, and so on. Okay, so rule number 5. Zeros to the left of the leftmost non-zero digit are not significant. So what does it mean? If you, for example, have written a number such as 0.01, the number 0.01 has only one significant figure, and that is the significance of the digit 1. Rule number 6. If a number is written in scientific notation, its significant digits are significant digits in its coefficient. So for example, if you have written the a number in scientific notation, for example, as 2 times 10 to the 5, the number 2 times 10 to the 5 has only one significant figure, which is 2. But if you have written the number 2.0 times 10 to the 5, the number has two significant digits. If you have written the number as 2.00 times 10 to the 5 in scientific notation, then it has three significant digits. Okay, so consider the zeros to the right end of a number and the left of a decimal place. That zero may or may not be significant depending on circumstances. Okay, so this topic about conversion will be discussed on a later occasion. The same goes with the temperature conversion and unit consistency and conversion.